Welcome, everyone, and thank you for joining us for today's webinar. It's part of an ongoing series developed as part of an FDA-funded project called A Targeted Learning Framework for Causal Effect Estimation Using Real-World Data. The focus is on topics in targeted learning, causal inference, and machine learning. Dr. Schnitzer holds a Canada Research Chair in Causal Inference and Machine Learning in Health Science. She received her PhD in biostatistics from McGill University in 2012 and was a postdoctoral researcher at the Harvard T.H. Chan School of Public Health in 2013. She also had the opportunity to study causal inference at UC Berkeley and the University of Pennsylvania as a visiting. Dr. Schnitzer's current research interests are causal inference methodology in pharmacoepidemiology, semi-parametric efficient estimation in longitudinal and survival settings, and meta-analysis. She currently holds an NSERC Discovery Grant, is PI on a CIHR project grant, and is a co-investigator on multiple CIHR-funded applied studies. Mireille, thank you for joining us today, and when you're ready, so are we.
Thank you so much for the invitation to contribute to this webinar series. It's really a pleasure. I love talking about this. So to jump right in, make sure I can, there we go. To jump right in, I'm going to be focusing on causal inference of longitudinal exposures, focusing on a specific type of marginal structural model. But I'm going to start with giving some intuition about why you might be interested in using these kinds of models and why other methods might fail. So standard methods that might be used for this kind of analysis can fail in certain settings, and so we'll be looking at why that happens. Then I'll be explaining 3 different algorithms for the estimation of the corresponding effects. One of which is an inverse probability weighting algorithm, so that uses propensity scores. You might be somewhat familiar with that. And then TMLE for longitudinal exposures, which is often called longitudinal TMLE or LTMLE. And then at the end, I'll be talking about a study that I did starting during my PhD that involves estimating the effect of breastfeeding duration on infant outcomes in the first year of life. So to acknowledge my collaborators for this application, this was joint work with Mark Vanderlaan, Erica Moody, and Robert Platt. And this was using a study by Dr. Michael Kramer, who is PI of the promotion of breastfeeding interventional trial. So I'll be talking about that later on in the presentation. So what are longitudinal exposures? We're interested in the effects of exposures that can be passive, means that we're interested in the effect of a treatment that was received or an exposure to an environmental condition or pollutant, something like that. But we can also look at effects of what I might call an active exposure. So prescription by a treating physician, we can look at effects of that on intervention and experimental design. So there are obviously a lot of different study designs that you can use, and then you can define effects in all of these contexts. And so I might use the word treatment instead of exposure sometimes, so you'll forgive me if I use those things sort of interchangeably. So a major point when you're designing a study from observational data, or when you're designing the data collection itself, we must consider exactly what exposure and what effect we're interested in. And what I find very important is to consider how this effect relates to a hypothetical intervention. And that's sort of a fundamental question to ask. So in particular, you might want to know, well, does the exposure that I want to consider vary over time? And so to make this a little bit more concrete, let's start by talking about a randomized controlled trial context. So this might be really familiar to you. So we have 2 effects that might be of interest, and one is the effect of assignment, or the intent to treat. And so this is just the effect of the randomized intervention. This is easy to estimate because, well, it's often easy to estimate because you have 2 groups that both represent the target population, and then we compare their outcomes, and then that compares, if there's a difference between the average outcomes, well, that's attributed to the intervention that was assigned. Another effect of interest might be the effect of being assigned to and then following the protocol. So that's sometimes called the protocol effect. But sometimes the analysis that is related to the per protocol effect doesn't actually estimate the thing we want to estimate. So sometimes it's called the effect of sustained exposure to the protocol drug. Now, due to non-adherence in an RCT, observed exposure may change over time. But we're interested in comparing what if everyone had continued to adhere to the protocol over time. How would the average outcomes compare at the end of such a study? So what's interesting here is we have a contrast between the observed data, the observed exposure pattern, and what we're interested in seeing, consistent exposure following the protocol that was assigned. So that's in the RCT context, but we may also be interested in estimating the same effect types with observational data. In fact, we might be interested in estimating exactly the same parameters, even though we don't have access to a randomization or randomized study design. And so I'm not going to go deeply into this, but in my applied work, I found that it's been very important to understand this idea. And so maybe you're familiar with the target trial approach, which has been proposed by Miguel Hernan and Jamie Robbins. And in particular, the paper cited at the bottom over here has been really helpful for me, because the first step in doing an observational study is thinking about the randomized control trial that we would have liked to do, and then emulating that in a certain sense. Okay, so here I'm just talking about it in the sense of we can define exposures along the same lines, even with observational data. So when I talk about causal inference, I often want to motivate why anyone should be interested in any causal approach. And so in particular, there's a bit of a contrast between what is typically estimated and then what is proposed to be estimated using quote unquote causal methods. So let's talk about some of the limitations, the potential limitations of standard conditional methods. So taking a simple example, later on I'll talk about motivations when you have longitudinal exposure, but for now, let's say we have a binary randomized treatment. This is like the simplest setting that you can consider. So there's no adherence, it's just single randomized treatment. You get 0 or 1. You have some covariates X that are measured. They are related to the outcome, so these are risk factors. And then you have a binary end of study outcome Y. This could be, yeah. So you might use a logistic regression to estimate a marginal odds ratio, for instance. And so that regression would look like this. I mean, really, you're just getting the odds ratio for the contrast between the two treatment groups. But I guess if you were thinking of modeling, then it would look like this. The exponential of beta 1 corresponds to the odds ratio. It's marginal because there's no conditioning on any covariates, but you wouldn't really want to do that typically in a randomized controlled trial. Okay, and why do we really not want to do that? Like, there's some issues about improving the empirical balance in the finite sample. But if we added covariates into that model, so we have, in the lower model, we have beta 2 times x, it actually changes the value of beta 1. So we don't call it beta 1 anymore, we call it beta 1 star. And so that odds ratio that you're attempting to estimate, that we often say we're targeting, has changed because we chose to adjust for some covariates, X. And A is randomized, there's no confounding. So that might be familiar to you. This is due to non-collapsibility of the odds ratio. There are other arguments for different models why the coefficient of treatment might represent a different effect depending on the covariates you adjust for or depending on the model that you select. But what's important to me, and so this is a compelling argument to me, although there's debate in the literature, not everyone agrees. So if you'd like to read a counterpoint to what I'm about to argue, you can look at the commentary in the American Journal of Public Health, cited at the bottom of the slide. But what's important to me is that if you have two different analysts who are analyzing the same data, and they both select different sets of covariates, maybe using statistical methods, or maybe just because they think that different covariates are important to balance over. Both of those analysts will actually be estimating different effects, not just they will have different estimates of effects, but what they're targeting will be different. So there's incoherence between the parameter of interest in the study, even though we're in the simplest setting in an RCT, and I think everyone should basically agree on what parameter would be of interest in this case. So what's important here, just mathematically, is that the conditional effect, the conditional odds ratio, exponential beta 1 star, has a definition that relies on the regression model specified. And then when we go into the observational study context, which is far more complex, you have the same issues and more. So in particular, now you're adjusting for covariates also to remove confounding. So there are different aspects at play, like what do we put into that model will really depend on what we think matters, and different analysts may have different opinions, or well, different like collaborative groups, let's say, may have different opinions about what needs to go in that model. Your study design might change, like the data collection in the study design might change based on who the investigators are. So all of a sudden, there's a lot of incoherence with respect to the analysis target. Okay, so this to me is compelling. I like the simplicity of saying, well, let's estimate that marginal parameter versus a variable conditional parameter. But the counterpoint addresses how it may not have a very, very large difference in the actual values of those parameters. So whether or not that's true, that's just, I like to give the counterpoint to my arguments. So that's an argument for why it is interesting to target marginal parameters when you have a binary single time point treatment. But the argument for why causal inference methods are important with longitudinal treatments is far more compelling. So as many others have done, I'll motivate this using observational studies of patients with AIDS and HIV. In the 1980s, there were short-term randomized control trials that evaluated efficacy, beginning with efficacy of emerging treatments for AIDS patients, and then later on for patients with HIV. So for instance, the first trial on AZT had a maximum duration of 24 weeks. And the outcomes of this trial included mortality and opportunistic infections. And so because it was short-term, of course, there was interest in seeing what happened longer term to these patients. And so many of them continued to be followed over many years in observational studies. And so a major biostatistical challenge emerged, which was how to evaluate the time-varying exposure to changing drug regimens. So as different drugs emerged, or as patients adhered or didn't adhere to what they were prescribed, the interest was to say, well, how do we compare any regimen of treatment? So there's this paper by Hoover from 1995 in Drugs that describes around the time that these analyses were occurring, the challenges of doing such analyses. And so two biases that he pointed out were longer survival increases the chance to begin therapy. Okay, and this would make therapy appear better than it really is. And so what's the resolution for this bias? Therapy must be modeled as a time-dependent covariate. And the second bias goes in the other direction. And that bias is that sicker individuals initiate therapy sooner than healthy individuals. So this is a problem with confounding. This bias goes in the other direction, so it makes therapy appear more harmful. And how do you resolve this? Well, you can incorporate covariates that measure patients' health status in order to try and unconfound the timing of treatment initiation with the outcome. So these are two aspects in the modeling of time-dependent exposures, but it doesn't address the specific effects that we want to estimate and modeling of such effects. So if we go into a little bit more depth, okay, so white blood cell count indicates disease progression in the setting, which can, through opportunistic infection, can lead to death, for instance. And so this is the very basic directed acyclic graph in the absence of treatment. Treatment in the past, and I think in some countries currently, would be initiated depending on the patient's CD4 cell count. Okay, so now we have the blue arrows pointing into A. What we're interested in estimating is actually all the pathways that come from A, the treatment, that go to the outcome, which in this diagram is death. So all the pathways include direct arrows going from A to death, and also pathways that pass through intermediate covariates like CD4 cell count. So all of that is part of the total effect that we'd like to estimate. And so what are the challenges here? So this is observational data, of course. There are confounders. So at the first time point, we want to estimate the effect, we want to unconfound the effect of A on death. And so we must adjust for CD4 cell count at the beginning of the study, okay, that precedes giving of any treatment. And then at the second time point in this very simplified graph, we also need to adjust for CD4 cell count in order to unconfound the second time point's treatment with death. But the problem is, so we definitely have to do that. But the problem is, once we adjust for CD4 cell count, and if we're adjusting through a conditional method that says, if we hold CD4 cell count fixed, then if we change treatments, then how much does it affect the average or the risk of the outcome? If we do that, then we're blocking the effect of A from the first time point that passes through CD4 cell count, and that leads to death later on. And so that's one reason why standard conditional methods would fail to estimate the effect of treatment in this context. There's another reason that I haven't illustrated in this DAG, and that's under certain structures, adjusting for a covariate that follows treatment can also open up biasing pathways. So typically, when we're interested in the effect of a treatment, we don't adjust for subsequent covariates that are kind of outcomes of the treatment that is given. See, in this case, we're interested in simultaneously estimating effects of a previous treatment and a future treatment. And so that's where the problem lies, or the complication lies. So if we're going to contrast conditional versus causal methods in this context, the conditional methods don't estimate a coherent effect. And what is this context specifically? It is a context where we have time-dependent confounders that are also mediators of the exposure effect. So part of the effect of interest passes through these confounders. So that's what I was talking about with the blocking of the part of the effect. So examples of conditional methods, to be precise, are mixed models, you might call them hierarchical models, which are typically used for longitudinal data. And then longitudinal survival models like cost proportional hazards models with time-dependent covariates. So both of these types of models condition on the time-varying covariates, and so it creates this kind of problem. And so in the mid-80s, Dr. James Robbins defined, or starting in the mid-80s, he defined at least two groups of models. The first is called structural nested models, and what I'll be focusing on today are marginal structural models. And so this allows us to define and estimate a coherent effect even with this structure. So it gets around this problem. So what are marginal structural models? They are models for conditional outcomes. Okay, what does that mean? So, counterfactual outcomes. So a counterfactual outcome, so here I have y1 and y0. Under a simple setting where we only have one binary treatment at a single time point, y1 is a counterfactual outcome that is defined as the outcome that would have occurred had we set A is equal to 1. And y0 correspondingly is the outcome that would have occurred had we set A is equal to 0. So regardless of the exposure that was actually received, we can define these two counterfactual outcomes. And so we might posit a model such as the simple model in the RCT case, which was for the marginal odds ratio, which is basically just a logistic regression with a single covariate, which is the exposure. Here, this is not a model for the observed data. It's a model for the counterfactual data. So it models, well, what if we had imposed treatment 0 or 1 on all the patients in the population? What would the expected outcome be? Okay, and you might have a first, well, you've probably seen this before since you've been following this webinar series, but you might say, well, that might be hard to interpret. But actually, it has the same marginal odds ratio interpretation as in the RCT, as we saw before. So this beta one we've already seen. And so if you can understand it in that context, and if it's useful in that context, then it would be useful even in the observational context when we're defining counterfactual outcomes. And now, what if we extend this to the multi-time point setting, which is really where marginal structural models become particularly useful? So here's it's still a fairly simple setting where we have baseline covariates x0, binary treatment at time 0. They have time updated covariates x1, and then binary treatment a1. And then some outcome y measured at the end of the study. So everyone has a measured outcome in this simple setting. Y00 is the counterfactual. So that's the outcome that would have occurred had we set both exposures to 0. And then Y11 is the outcome that would have occurred had we set both exposures to 1 over time. And so then similarly, we could define a logistic regression that conditions on just those two covariates, which is the fixing of exposure at time point 0 and 1. And then we can see how the expected outcome, or the probability, since y is binary, then it would be the probability of the outcome, how it varies when you manipulate the exposures. And so if you really want to understand this well, then you would say, well, what if we had randomized treatment at time 0 and 1 and fit this exact model with the observed data? That would be estimating the same two odds ratios. Okay, so I wrote here, this is what we would get in a sequentially randomized control trial. Okay, and so the idea is that by defining counterfactuals, we can also define the models that we want to estimate, even with observational data. It's easy to estimate this with randomized data in a perfect setting, and it's doable in the observational setting as well under a series of assumptions. But bringing this back to the application, we're interested in longitudinal intervention. So this is like a factual world where we're able to do this. In this world, there's no confounding because we set A. A is something that was fixed, and so there are no arrows going into A. So we no longer need to adjust for CD4 cell count in order to unconfound the treatment. And in fact, if you did adjust for CD4 cell count, as we saw before, you'd block part of the way. And so when you're interpreting the model, you're interpreting under this diagram of a hypothetical data structure where A is sort of independently set, and it is affecting all downstream variables like death and CD4 cell count. So this corresponds to the marginal structural model, or the structure kind of underlying the marginal structural model. But I want to talk specifically about the simplest kind of marginal structural model, which have been called saturated. So specifically, we just want to estimate expectations or probabilities of the outcome under fixed sequences of exposures. Okay, so fairly easy to understand. There's no actual modeling involved here, so it's completely non-parametric. So the interpretation is the expected outcome or risk of the outcome if we set exposure at the two time points to 0, 1, 1, 0, 0, 0, 1, 1. So that's 4 different parameters to estimate. You don't have to estimate all of those parameters. You can, for instance, choose only treatment regimens that correspond with guidelines. So for instance, once you start medication for HIV, you must continue if that's the guideline, and you're like, I want to know what if people follow this guideline, would it be effective? Then you would only estimate regimens that had monotonic exposure patterns. So for instance, A0 is equal to 1, then necessarily A1 is equal to 1. So you'd really only want to estimate Y00, Y01, and Y11. We can also fit any kind of marginal structural model under guidelines that depend on covariates. So in this case, you might say, okay, well, the guidelines say to start when CD4 cell count drops below a certain level. So you could say, well, I want to know if I follow the guideline, be treated if your CD4 cell count has dropped low enough, or if you were previously being treated, it is still monotonic, we could do that too. So that's called a dynamic treatment regimen. So that was my motivation for why you might be interested in estimating marginal structural models in contrast to standard regression methods. So I'm going to motivate the rest of the talk with the study that I contributed to, which was the promotion of breastfeeding intervention trial with PI Mireille. So in this study, maternal hospitals and polyclinics were randomized to receive lactation management training, which had the goal of increasing or prolonging the duration of breastfeeding, kind of increasing uptake of breastfeeding. So there was recruitment for the study in Belarus from 96 to 97. And the study hospitals, the study recruited pregnant women who intended to breastfeed, and then and only followed up with healthy full-term singleton infants from birth. So all the women in the study attempted to initiate breastfeeding, and then the durations varied. The question of interest is, did the duration of breastfeeding impact gastrointestinal infections or hospitalizations in the first year? Okay, so I'm going to introduce the full complexity of this study, or the way I addressed it later on, but for now we're just going to use that sort of as a general example. So the data used for the exposure, you can have like mixed feeding, but the data used for the exposure was, is the baby still breastfeeding, yes or no? So at every time point, this was asked, and the data was actually much finer. In particular, they had like roughly or the reported time of when breastfeeding ceased. But for us, we just used the simple exposure of yes, no. And so to simplify the data structure greatly, for now, let's just think of 2 time points for this data. So you have baseline covariates L1, you have the first time point's exposure, which corresponds to continued breastfeeding at month 1. So that's the observed exposure. And then L2 is the time updated covariates. A2 is continued breastfeeding at month 2. That's yes or no again. And then we have the outcome, which is gastrointestinal infections, yes, by month 2. Okay, and so we want to contrast different durations of breastfeeding. And so in particular, we want to know what's the risk of infection under imposed durations of breastfeeding if the entire population in this study, or targeted by this study, had followed those durations. So for instance, we can estimate the probability of an infection under not taking up breastfeeding, like failing to initiate breastfeeding. Or we could estimate it under breastfeed until 1 month and then stop, or breastfeed until at least month 2, and then the outcome would be measured after that. So if we contrast these things, well, then we can access the time-specific effect, or we can contrast different durations of breastfeeding and see whether there's an impact on this outcome of interest. So the big question is, well, we can define these marginal structural models, and then I claim that we can maybe estimate them using observational data, but you actually can't always. You need a bunch of assumptions to hold in order for us to go from the observed data to the counterfactual models. So the important assumptions that must hold are no interference. So this means that the potential outcomes of one subject do not depend on the exposures of other subjects. And in this case, it means that one infant's breastfeeding does not impact another infant's probability of hospitalization, given in this context. So we're not super worried about that assumption holding. The next one's a bit more dicey. So we have sequential consistency, which means that when we observe a certain exposure pattern, then the exposed outcome is equal to the counterfactual under the same imposed exposure pattern. So this means that imposing breastfeeding up to time t would have resulted in the same outcomes that we observed when we measured that the breastfeeding lasted up to time t. But you may have noticed that there's a little bit of imprecision in how duration of breastfeeding is considered in this analysis. So we'll say up to month 1, up to month 2, meaning that there was, if they stop breastfeeding, it's in between those 2 time points. And so in order to believe this assumption, we have to believe that that granularity doesn't really matter, and that what we observe pretty much corresponds to what we would have observed had we imposed these patterns. The third assumption is probably more familiar. No one measured confounders of both treatments, both times of exposure and the outcome. And so this corresponds to having no other confounders besides what was measured in L1 and L2, and A1 can also be seen as a confounder of A2, so it's beyond that. And then for the first time point, no unmeasured confounders of A1 and Y, we assume there are no other confounders besides L1. And finally, we also have to have sequential positivity, which means that essentially no one was ever contraindicated from continuing breastfeeding conditional on the confounders L1 and L2. And more specifically, that means that the probability of continuing breastfeeding, so had we already been breastfeeding, then continuing, is bounded between 1 and 0. So it doesn't reach 1 and it doesn't reach 0. And then the first time point, it's the same idea, or the probability of reaching that first time point or continuing breastfeeding up to the first time point conditional on L1 is also bounded. So what you might know here is that we're only considering exposure patterns that involve durations. So the monotone breastfeeding patterns, once you stop, you stop. This would be the typical pattern that we would observe. It would be very unlikely to stop and start breastfeeding again. But even if some manage to do that hypothetically, this is really what we're interested in different durations. And so that's what we consider under sequential positivity. So now I'm going to describe estimation. So if all of those assumptions hold, or if we're comfortable with them to the point that we think that we should proceed to estimate something that's interpretable, like a marginal structural model, we might use something like inverse probability weighting. So I basically have one slide for each algorithm. So the goal here, for instance, would be to estimate the probability of an infection under continuing breastfeeding for the first 2 time points. Okay, just as an example, we can do this under any exposure pattern of interest. So how do we do this? We have 2 regressions, so it's like having 2 propensity scores. So we need to estimate the probability of being exposed at the first time point, conditional on the baseline covariates. And then we need to estimate the probability of continuing to breastfeed at the second time point, conditional on baseline covariates, the time updated covariates. But also, so we're setting A1 equal to 1. So saying, had we already been breastfeeding at first time point, well, what's the probability of continuing? So both of these are estimable with regression methods, for instance, and it's not specified exactly how you estimate these things. So there's flexibility here. The next step is to calculate a weight for each person. We're only going to take participants in the study who actually did continue to breastfeed for those first 2 time points. So we're subsetting on the data. We're taking people with A1 is equal to 1 and A2 is equal to 1. And then we assign a weight for each of those people, which is 1 divided by the product of the G's. And the final step is to run an intercept-only regression using those weights on the same subset. And you could repeat this procedure for all the parameters of interest, for all the exposure patterns. It would change what the specific probabilities have to be. These probabilities would have to correspond to the exposure pattern of interest. So for instance, if it was y0, 0, then we would estimate the probability of A1 being equal to 0, and then A2 being equal to 0, conditional on A1 being equal to 0 for G2. Okay, but it's essentially the same thing. So that's what I would consider to be a simple algorithm. And that's part of the main strengths of inverse probability weighting. The idea that I didn't really describe here, that you may have seen in another webinar, is that you're essentially reweighting the population to get a pseudo population was actually randomized. And so all of the modeling that you do with those weights represents the marginal structural model, which is interpretable under the randomization of patients where there's no confounding. So that's fairly intuitive. I don't know why I start with weaknesses on these slides. I guess I'm negative, but so the weaknesses of inverse probability weighting are that it's inefficient, first of all. And in a practical sense, it often results in pretty large variance relative to other methods. It can also be unstable. So sort of have like randomly large bias or large error in finite samples due to large weights. But though this can be helped with weight stabilization in certain structures, and it can also be helped with some ad hoc methods. There are also no established properties under general machine learning for propensity scores. So the ability of IPW to estimate the parameter of interest relies not only on the causal assumptions, but also on the correct modeling of those propensity scores, which is why you might be interested in using some machine learning approach like superlearner in order to get a better estimate of those quantities, which is reasonable and sometimes might work very well. But in terms of formal properties, there's no established asymptotics under general machine learning. So there's a limit to how flexible you can be. There's a pretty strict limit to how flexible you can be when you're estimating those propensity scores. The strengths are, like I was mentioning, it's intuitive. You can look at the weights directly and say, do these weights or are they manageable? And that's sort of a interpretation in order to diagnose, well, is this working well? There's simple ad hoc weight management strategies available, like truncation, where you just kind of arbitrarily reduce some of the weights of people. This could create bias, but it can possibly reduce a lot more bias if that bias comes from instability, which is due to a lack of data for some strata of the covariates. This method can also easily handle longitudinal censoring, and it can be directly used to fit more complex marginal structural models without much problem. So another method that can be used to estimate marginal structural models involves outcome modeling. And it's available through the G formula, which was developed by Jamie Robbins in 1986. And so G-computation corresponds to using the G formula to do estimation. One particular formulation has shown to be very easy to use when there are multiple time points and time-dependent confounders. And so this was described in the paper by Bang and Robbins in 2005. And it sort of underlies the LTMLE approach that we'll see in a few slides. So for estimating that parameter of interest, probability of y1 equals 1, it requires two quantities. The first is the conditional expectation of the outcome under setting the exposure to pattern is of interest. So in this case, it's setting A1 is equal to 1 and A2 is equal to 1. It's conditional on the covariates up to the second time point. So this regression method, you plug in the exposures and then you predict under the counterfactual exposures. And this gives you this quantity that we'll call Q2. And then we define Q1, which is, so we take that outcome, that prediction from the first expectation, we plug it in as the outcome. So it's nested, okay? So then you have that outcome in the exposure, and so this quantity Q1 is just defined as the conditional expectation of Q2, conditional on covariates up to time 1, and also setting the first time point's exposure to what's of interest. In this case, it's 1. And then under the causal assumptions, the expectation of Q1 is equal to the parameter of interest. So that's it. So in terms of estimation, you just have to estimate these two quantities. So for Q2, you'd run a regression of Y on the covariates and exposures. You would set the exposures to 1, you'd predict, then you'd take those predictions, you'd run a second regression on L1 and A1, then you'd set A1 to 1 to make predictions, and those would be predictions of Q1, and then you'd take an empirical average of Q1. And so that's how that algorithm goes. And this would give you unbiased estimates if you correctly specify these two regression models. And so some weaknesses of G-computation. So IPW is really easy to extend. I found that the G formula, G-computation, are more challenging to extend to different outcome types, which has limitations in terms of software development. It's just harder to develop general algorithms that can be easily used in application. There's, again, no established properties under general machine learning for Q1 and Q2. These need to be essentially correctly specified at models that satisfy parametric rate. It also relies on the correct specification of the nested expectation, which is like a harder model to conceptualize. So maybe Q2 is more interpretable. It's just a regression of the outcome, but Q1 is a nested model, which is harder intuitively to specify. But the strengths, it's efficient. It's a maximum likelihood approach for the relevant parts of the likelihood. If you implement it completely parametrically, It has a quick runtime, so if you use it for exposures with multiple time points, basically one model per time point. So it's scalable, and it can easily handle longitudinal censoring again. It can also be used for general marginal structural models. So finally, we get to longitudinal TMLE. So the algorithm for saturated marginal structural models was developed by Mark van der Laan and the organizer of this very web series, Dr. Susan Gruber. It involves modeling all the components needed for IPW and G-computation. So those are all the components we've already seen. The G components and the Q components all need to be estimated. And the basic idea, so it's similar to the standard idea of TMLE. I like to say that it improves upon the estimation of QT, so the two Q quantities, using information from the propensity weights. So basically shares information between those two quantities in order to hopefully give you an optimal estimate of the parameters of the marginal structural model. Those are the target parameters. So the motivation here, like why do we need to do something that's not IPW, not G computation? Well, we really want to take advantage of the double robustness property, which in this case corresponds to if we can correctly model all of the G quantities and or all of the Q quantities, so those are two groups, you either have to get all of one or all of the other right, then you will have consistent estimation of the parameters in the marginal structural model under the causal assumptions. This is connected to the theory which allows us to incorporate machine learning in the estimation of these quantities. So in practice, it just works much better. So if I run a simulation study and I want to see, okay, well, which methods are robust if I use machine learning? Well, methods like LTMLE would be the most robust that I have experience with. So we want to use machine learning because we avoid parametric modeling, and that gives us better consistency guarantees. If we're flexible enough, then we can say, yeah, then our estimates of the parameters of interest will be consistent because we're more likely to correctly specify the models for G and Q. Another good thing is that it's efficient, and so that has a specific definition, but I'll just say here it beats IPW when all are correct. So here are two slides actually for the algorithm. Each slide corresponds to one time point. So the first must estimate the two propensity scores. Then we estimate Q2, which is the regression of the outcome once you fit A1 is equal to 1, A2 is equal to 1, and predict. So then we have estimates Q2 hat. We want to potentially improve upon those estimates. And so we do so by using the propensity score weights. This we'll call W2. It's at the second time point. It's 1 divided by the product of the propensity scores. Then you run a weighted logistic regression of the outcome with an offset term, which is the logit of the initial estimates of Q2. And you do this in the subset of the people with the exposure pattern of interest. So you have an intercept in this regression, and we'll denote that intercept epsilon2 hat, or that's the estimate. And then you update your Q2 estimates by basically predicting from that last model, which corresponds to setting Q2 star equal to inverse of logit of the offset plus the estimate of the intercept. Basically, it allows you to shift the estimates Q2 by the intercept epsilon2. So if you have a 0 value for the intercept, it's suggesting that the propensity score weights are not helping for the estimation of the target parameter. Your initial estimates were good enough with respect to the information being provided by both models. So if you get a 0 here, you basically come back with your initial estimates of Q2. So that would be in the context where possibly you correctly specified the initial regression model for the outcome. Okay, and now because longitudinal, we have a second step for the algorithm. So this is where we have an initial estimate of Q1. basically we take our best estimates of Q2, which is Q2 star hat, and we run a regression on L1 and A1, then we set A1 to 1 and make predictions. So that gives us our initial estimates of Q1 hat. We basically do the same algorithm, except now we're only going up to the first time point. So we have a weight, which is 1 divided by the first propensity score. We run a weighted logistic regression. Now our offset is the logit of the initial estimates of Q1. Our outcome is Q2 hat star. We run this in the subset of people who followed the first time points exposure pattern of interest. We have the estimated intercept from this model, which is epsilon 1 hat, and then we shift our initial estimates. And this gives us the updated estimates Q1 hat star. And the final step is just taking the average of Q1 star. Okay, and so that's like the same as in the G-computation. You basically have Q2, then you get Q1, and then you take the average. And so that gives you the estimate of your parameter of interest. So key strengths and weaknesses of LTMLE. The weakness, I would say, is it's more challenging to extend to different outcome types, which again sort of impacts software development. So I'll talk slightly more about this for our study. Longitudinal accounts and survival, it's a little bit of a different algorithm to implement. Weights can cause instability here as well, and they must be diagnosed like an IPW. And I find also that there's multiple moving pieces that you need to check in practice. I emphasize this a lot with my grad students. I say, there are so many things that you estimated. You need to kind of see how those models were fit and see if it's giving you reasonable results. And then the strengths for what I mentioned previously, the same as for other TMLEs. You have local efficiency in the semi-parametric model space. It can easily handle longitudinal censoring. It can be used for general marginal structural models. And there's a paper by Peterson 2014 that talks about the survival setting, and can formally incorporate machine learning. So for the next 5 minutes, I'll just kind of briefly talk about the application that we did in the PROBIT study. So this was a cluster randomized study, because it was like the intervention of breastfeeding encouragement was assigned to the hospitals or hospital centers. And this was important because all previous evidence of the protective effect of breastfeeding came from observational data. So the original study established that this intervention had an effect on the duration of breastfeeding. So it was meant to encourage breastfeeding. So it was effective in that sense, but it also had an impact on infections. So our goal was somewhere in between. It was to say, well, is it the breastfeeding itself that had an effect on infant outcomes? Which is a separate, so it's kind of an intuitive interpretation of the original study, but the original study did not directly address this question. And so there were 6 follow-up visits in this study. It measured baseline data, follow-up data that included the duration of breastfeeding, growth, illnesses, and hospitalization in every time period. There were 31 clusters and a total of just over 17,000 mother-infant pairs who had complete baseline data. There's very, very little missing baseline data. So this was the structure of the data. So you can see that it's more complicated than what we were previously using, but it's a similar idea. So you have exposure at every time point. You have covariates that are updated at every time point. And now we've added in censoring. So basically patients enroll in the study. They may stop participating in the study at any time point. If they continue, then we can measure things like their hospitalizations between study visits, just by asking, was your child hospitalized since the last visit? And then at every visit, they're asked if their baby is still breastfeeding. Okay, and so on. And then at the end of the study, we basically tally how many periods of hospitalization there were, how many infections were recorded over time. So these are count outcomes, which makes it a little bit different than other types of outcomes. So for instance, we are interested in comparing different breastfeeding durations. Here's an example. We might be interested in contrasting outcomes under duration past 9 months versus up to 2 months. Now this corresponds, the latter corresponds to the observed exposure where you stop between 2 and 3 months, because this structure doesn't give us a more refined exposure measure. So some of the additional complexities that we addressed, I'm not going into any detail here. There's there's many more details in the paper in the book chapter. But this is longitudinal count data. So when you're estimating the Q quantities, you're conditioning on updated covariates up to a given time, which means that only part of the outcome is random when conditioning on that. And so it might change how you model those quantities. So standard algorithms maybe shouldn't be used directly. There's also, because this is a clustered study, if you want to take that into account, and probably is a good idea, you can use a cluster bootstrap to estimate variance, and we also developed a closed form asymptotic approximation for the LTMLE. There was also, as you saw, longitudinal censoring, which adds in additional nodes where we want to impose intervention. In this case, it would be imposing the intervention of no censoring. So we want to estimate the marginal structural model parameters under no censoring, and then following those different breastfeeding durations. So here are some results for hospitalization outcome. Essentially, you can see that we have different estimates here. All of them suggest, all the point estimates suggest for G-computation, IPW, parametric TMLE, TMLE with superlearner, they suggest that continuing breastfeeding to between 3 months versus 1 to 2 months has a protective effect. And if you go further, you say, well, how about if you continue from 3 to 6 months to 9 months? Is there even more of an effect there? And almost all of the methods said no, that there's no difference between the outcomes of those exposure groups, except for IPW, which suggests that extending breastfeeding is harmful. Which is interesting. I would exclude that as a hypothesis. So it makes it less credible. And so you can see that in this corresponding plot, as breastfeeding duration increases, the marginal expected number of hospitalizations decreases up to a certain time point, up to stopping between 3 and 6 months. Now, what's interesting is that we don't get the same results for gastrointestinal infections, where we did see some effect continue past 9 months of continued breastfeeding. So we did a simulation study, but it's less important. So overall, causal inference methods are warranted, in particular in settings where exposures vary over time. They're very easy to motivate in these settings. So I would always use causal inference methods in this kind of a setting. And I do that in practice too, with my applied collaborators. Choosing the counterfactual parameters of interest is an important part of the analysis. In fact, sometimes I think my major contributions to studies are helping them design their observational structure and picking the parameters of interest that correspond to a randomized controlled trial, to those you would estimate in a randomized controlled trial, which sometimes changes the exposure of interest, but always corresponds with something clinically interesting. Obviously, that would be a criteria. All of these methods, just to remind again, they rely on a set of assumptions, the causal assumptions, and these can be discussed and refuted. But even if you say, well, this assumption is not likely to hold, you might also want to say, well, how much bias is that likely to cause? And you can sometimes approximate that amount of bias. And then we saw why LTMLE is desirable due to its efficiency and ability to integrate machine learning methods. Even though it may need some non-standard implementations under some data structures. And so here are all, so you have the slides, here are all the references that I did over the slides, and here is my funding statement. Thank you very much.
Thank you, Mireille, for that tour, that introduction to longitudinal data analysis with TMLE and with these other causal methods. We have 3 minutes left. If anybody wants to type a question into the chat window, you can. And while we're waiting for that, I want to say something to the audience members. I want to say that when I first heard about this back when I was in graduate school, let's say 2009 or 2010, I walked out in a daze. L, Q, G, T, and it's just, it was a little bit incomprehensible. And so if that happened to you today, don't fear. It's going to turn out that this is used sort of in a lot of the causal literature, not just for targeted maximum likelihood estimation, but also like in the work of Robbins and Hernan. And it gets easier. The L's are really just the time-dependent covariates that you observe and record. Um, the A's are the treatments over time. And if at FDA you're only ever interested in point treatment, you still have to think about loss to follow up at different time points, which Mireille represented as those C nodes, or you can just, we call them also intervention nodes, the A's and the C's. So you're going to hear more about survival analysis in the next one or two webinars in the series. And you'll hear this notation again, and it will become more familiar. And I think you got a really nice intro on motivation from Mireille. Are there any, I don't see any other questions. So Mireille, I think I will just say thank you so much for this and for agreeing to share the slides and have the talk posted publicly. We do have a message. Thanks for the interesting talk. I'm curious whether the sequential positivity assumption can be checked in the data sets. I'm thinking for data sets with many time points, it may be violated. For example, sicker patients are more likely to receive treatment.
Yes, that's a great question. It can be investigated, whereas the no unmeasured confounding assumption can't really, like it can't be empirically investigated. So you can definitely estimate those propensity scores over time and see if you get values that are 0 or close to 0 or 1. And that can occur due to, and then you can think of, well, why is this happening? You can look at the model fit and say, oh, it's because people with this covariate always stopped breastfeeding. And that would be like a real positivity violation, but sometimes it could be like caused by, oh, we just didn't measure a lot of people continuing breastfeeding who looked like this, who had these covariates. And so absolutely. There's also additional things, I know we're out of time, but there are also additional aspects involving positivity violations. I actually have a tutorial coming out in Statistics in Medicine that talks about how to approach that from this framework. So I guess you can look out for that soon.
Thanks again, Mireille. We really appreciate you being here.
Thank you. It was a pleasure.